Okay, so today we will talk about one type of sensors, temperature sensors specifically, which is the thermocouple. So we need to understand how they work, how we do the measurement, and how we do the calibration as well. Okay, so let's move on. Okay, so how thermocouples work? What are the basic things? When we have a wire, and this wire is in one point connected to a hot point, and in the other end it's a cold end. Okay, so either I am intentionally measuring something very hot, so that will be my hot point, and my cold point will be like my room temperature, or it's the other way around. I'm measuring something very, very cold, minus 50, minus 60, and my hot will be my room temperature. Where is my measuring system? So it could be this way or that way. Anyway, so when we have one end of the wire is hot, the other end of the wire is cold, there will be electrons at the hot end are more thermally energized, and they are than the ones that at the cooler, because when you have heating, those electrons becomes more and more energized, and they will start to diffuse the electrons, moving from the hot area to the cold area. And once this happened through the wire, then you will have a potential difference between the two ends of the wire. Okay, so you have this wire. This is a wire. Okay, so at one end it's a hot point, and at the other end it's a cold. So between these two, the two ends, there is a potential difference. Now this voltage, which we call it the Seebeck voltage, this is the effect called the Seebeck effect. We cannot measure it. Why we cannot measure it practically? Because remember, one end of the wire will be at, let's say, inside the furnace. The other end will be in another room where you have your measuring system. So it's a huge distance. How you can measure a difference between these 2 points? How you can bring a voltmeter and you come with the two terminals to measure the voltage? You cannot do that. So it's not possible to measure the temperature using only one wire. Now, there is something interesting here, that different metals, different alloys, or semiconductor materials can be used in the thermocouples. How is that? Now, each metal or alloy has its own thermoelectric sensitivity, or Seebeck coefficients. So if you have aluminum, copper, each material has its own Seebeck coefficients, and we will use this phenomena to our advantage to develop the sensor. Now, this Seebeck effect can be positive or can be negative. Let's have a look to some examples. For example, here this is aluminum. The Seebeck coefficient is 3.5. What does this mean, 3.5? This is the unit of microvolt per degree centigrade. So it means that you will have a 3.5 potential difference between the two ends for every increase by 1 degree centigrade. So if you have, let's say, 10-degree increase, you will have 10 times 3.5, which is 35 microvolt. Now you notice here, for example, aluminum is 3.5, cadmium is 7.5, copper is 6.5, germanium is 300. So you have different materials, you have different values, which is very interesting. Now, have this in mind, and let's move on. Now, how we can construct such a sensor that can be used in the measurement. So what we do here, we will have two different metals. Let's say that I have in the first one aluminum, Al. And aluminum has a 3.5. So this is 1 point and this is the other point. So there will be a potential difference of 3.5 between the hot to the cold, 3.5. So here, from here to here, it will be a 3.5 volt. Now, if we connect another metal, okay, to the same point, so they share the same point here, and let's say this is iron, for example, or gold. So here, this is iron. Now, for the iron, the voltage from here to here, it is 19 volt. So you have a potential difference between this point and this point as 19 volt, plus, minus the 19 volt. And for the aluminum, it is from here is 3.5 volt. Okay, now there will be a potential difference between these 2 points, which is the difference between these two. So if I manage to have these two conductors, different conductors, they have to be different conductors, connected at one point, and here we have the hot source. There will be a potential difference between this end to the other end of the first metal, a different potential difference between this and the end of the second metal. So at the end of this, there will be a potential difference that we will measure. And this is an example of uh, thermocouple. So here you can see this is the end. The two metals are uh, welded together. And here is the other end where the two metals are not welded. They are separate. You have two, one and two. And we measure the voltage here. So this end will be connected wherever you want to do the measurement. And at this end, you will connect your voltmeter to measure the voltage to know how much voltage between these two metals has been produced. So this is as simple as it look like here. So for example, here, this is one end is nickel chromium, the other one is nickel aluminum. And at 300 degrees centigrade, you will have a 12.2 volt, sorry, millivolt generated. So one interesting thing here we noticed, this is the voltage is extremely small, and this is because the Seebeck effect itself, it is in microvolt per centimeter. So here for 300 degrees centigrade, you are getting 12.2 millivolt. So if you connect, this is the end where the two wires are split from each other, connected to a voltmeter, and this is the end where you connect it to the hot spot. Then you will see a voltage here that correspond to the difference between the sensitivity of both wires. Now, so this is the basic principle of the Seebeck effect. Now we want to use this to be able to measure the temperature. Always remember, a sensor change a physical phenomena into a voltage. Now, the thermocouples do that directly. If you recall, in the strain gauge, the change in the strain is converted into change into a resistance that I need to put it on a Wheatstone bridge that will convert the change in the resistance into change in a voltage. So you measure the voltage. Here we get the measurement in the voltage right away. But still, there are certain issues that we need to solve. I measure a voltage. How I can correlate this voltage to temperature? Remember, I don't know this temperature. What I can see only, or what I can measure, what I can sense is only this 12.2 volt. So how I can convert this? This is what we'll be discussing now, and we'll see how we can do this. This is the most important thing when it comes to the couples. So here again, here is the voltmeter. Here there is no voltage because the 2 points are attached to each other, so they are like short circuits. So there is no voltage here, but there is a voltage between this point to this point, and that point, and then you will have here the voltage difference that we can measure. Okay, now if I come and use in one conductor copper and in the other one gold, what do you think be the output voltage regardless of the temperature I apply? Let's see if you understand. Zero. Excellent, Grace. It will be zero. Why? Because both the copper and the gold, they have exactly the same sensitivity. So you will have at the end the same voltages. So the voltage difference will be zero. So you cannot use two metals with the same Seebeck coefficients. They have to be different. And the more the different is, the better you'll be your sensor, because you'll become more and more sensitive, as we will see. Okay, so these are the basic information that we need to use. Now, as we said, that the junction point will be, this is the hot or cold temperature point. It depends what is your interest. I have showed to you at the beginning of the set of notes a sample of cement, a sample of concrete. One of them is in the oven, one of them is freezing temperature. So you could be interested to measure a hot temperature or a cold temperature. It's up to you. And then this is where you want to have the common point there, and the other point will be at a different temperature, usually the room temperature, where you have your measurement system. Now, so there is a voltage that is a function of a temperature. This voltage, it can be represented as a polynomial. So V is equal to A1, a constant, times T, the temperature, plus A2 times T square, E3 times T cube, etc. So this mathematical relation can be used to convert the voltage into temperature. Okay, so first of all, we can notice here it's nonlinear, the relation. Okay, and many thermocouples, they have 7th to the 9th order polynomial, which will make it very hard to solve. Okay, so these values depends on the metal. Remember, you you have measuring a voltage and you want to find the temperature, and this temperature is in the 9th order polynomial. You need to solve this. You have to use some numerical method techniques. We will not go into this, but we will show you a much simpler way to do the measurement. Now, the thermocouples are classified by their type of the metals, and this will give us different characteristic. The first one is the temperature range. Each type of thermocouples will have a certain range, certain sensitivity, and certain accuracy. So it depends on your application. The thermocouples need to be selected as per this. These are the most common metals used for the thermocouples: chromium, copper, nickel, iron, etc. And there are some charts that provide the thermal response of the thermocouples. We'll come to one of those charts. Okay. Now, as I mentioned, in many cases, the distance between the sensor and the measuring device could be tens of meters. For example, you want to measure a temperature inside a furnace. You will not have your measuring device close to the furnace. You will damage the measuring device. So the measuring device will be far away from the furnace. Now, you don't want to have a thermocouple that goes tens of meters. Why is that? Because it will be very expensive. The metals of the thermocouples is very expensive. So what we need to do here, we need to add some sort of extended wires. And to do an extended wires, this wires has to be compatible with the sensor material. Otherwise, the calibration that you want to do, it will be ruined. So you have to make sure that you select the specified material to be used along with the sensor. And we will see for each type of sensor what is the type of the wires that need to be bought along with it. Now, the most common thermocouples, they are called the T, J, and the K type. The one that I just showed you here, this is the K type. Unfortunately, we had an experiment in the lab to use the thermocouples, but unfortunately we cannot have it because you need some specific equipment to do the measurement, and these devices, they are not available They are available online, of course, but you need some specific equipment to use them, which you will not have them. Now, what we see here in this graph, the x-axis is the temperature. So in each one of those, you will see a range of temperature it can measure. And in the y-axis is the voltage through the whole range, the whole spectrum. Okay. Now you see some of them are linear, more linear, and some of them they are completely non-linear devices. Some of them are they having strong slope. Some of them they have slow slope. Now, if I ask you if you have the choice to select, which one you select? Will you select the K or the R? If you are, if the assume they are have the same temperature range, which one you think is better for the application? K. Why K? I agree. I agree with everyone. It is the K one. Why the K? Higher resolution, more sensitive. It is more sensitive to the change. You see here, for example, if I change the temperature from 1,000, let's say, let's take something common, from 1,000 to 1,250, you have 10 millivolt change here. The volt change by 10 millivolt if you go from this to this. Now, if you take the same thing for the R, you see the change is 2 or 3 millivolt. So it is much less sensitive. I want the sensor to become more and more sensitive. And keep in mind, the voltage is still in the millivolt. And you need something else also to be able to do the measurement, which is the amplifiers. We need to amplify this voltage because having something in the millivolt range, your device will not be able to detect it properly. But if you can magnify this 100 times, 1,000 times, then you will measure things in terms of volt, not in terms of millivolt. And that's why it's very important in the measurement system to deal with amplifiers. And these are the ones that we'll be discussing next week. Okay, so here the type T thermocouple has a limited use because of the range. See here the range is from 0 to a few hundred, so it has a very limited use. Okay, now the delta V by delta T is very important. This is the sensitivity of the sensor, and the higher the delta V by delta T, the better will be your you'll be your sensor. Also, thermocouples with limited temperature range, they have better linearity, which is something also very important. And here we are showing only the temperature until 0, but you can see you can do the measurement of the, below 0 as well. This is a typical data sheet for a K-type thermocouple. So here in the positive, you have chromal. This is a type of an alloy. Negative is aluminum. This is can be represented by an 8th degree polynomial. Applications, this is very important because selecting the thermocouples or the temperature sensors in general, it depends is what is the range of your measurement. That is the most important thing. What is my temperature range? You will notice here that the thermocouples go through very extreme temperature. Other sensors give you better accuracy, more sensitivity. However, they cover smaller range of temperature. So it depends on the application how you can select your sensor. Now, between minus 200 to 1300, the for for this full temperature range, you have a swing voltage of only 56 millivolt. Meaning, if you change the temperature from minus 200 to 1300 degrees centigrade, the change in the voltage that you will notice is only 56 millivolt, which is, as I said, this is one of the drawbacks of the thermocouple. And this is why the thermocouple is used for extreme, very high temperature, and you have to use them with some sort of amplifier. Now, as I mentioned that If the sensor is far away from your measuring device, you need some lead wires to connect them. And here it's specified for the positive, you can use iron or copper. For the negative, you can use copper nickel alloy or constantan. So these are the material that can be used to as an extension for the wire. Now, our last point. Now, you cannot just simply, to measure the temperature, connect your thermocouples and get the voltage and that's it. Why? Because the voltage that we are measuring actually, it gives you the difference between the hot point and your reference. So what you are measuring is the temperature difference, but it's not actually giving you the absolute value of the temperature. Meaning, your sensor here at 100 degrees centigrade, let's say, and your location at 24 degrees centigrade. What you are measuring, you are not measuring the 100, you are measuring the temperature difference between the two. So your sensor will sense there is a temperature difference between 100 and 240. Okay, so you are not actually knowing the exact temperature, rather than the reference. Now, this is unknown to us. We don't know this. And if this is also unknown to us, so this temperature that you are measuring is meaningless. Why? Because, okay, I know that the difference between the point of interest and my location is 70 degrees centigrade. But what is the actual temperature there? Then I have to do some sort of correction. Okay, so this is very, very important. Again, you are measuring here. This is your measuring point, but you are measuring at this point. So what you are measuring is the difference between this point and that point. What I want is to know this temperature, not the temperature difference. So how we'll do this? One way, and this is an old way of doing this, they will come at the reference point and they put the leads in ice. Okay, so if you put them in ice, you know that this is 0 degrees centigrade. So you know you are forcing your reference temperature to become equal to 0. So then whatever you are measuring as a temperature difference, it will be because whatever you are measuring minus 0, so it will be whatever you are measuring. So here the V that you are measuring is the difference between the hot and the reference. Our interest is in the hot temperature, which is what you measure plus the reference. So if I force the reference to be in ice, then this will be 0. So whatever voltage you are measuring is actually the hot point. Now you can tell that's not convenient to have an ice pocket with you in the field all the time. That's not really very, very convenient. This is used in labs under controlled conditions long time ago. But what if I know the temperature here using another sensor, simpler sensor, cheap sensor that can tell me what is the temperature, then the voltage at the hot equal to the V measurement plus V reference. And usually, as I said, usually the measurement system at room temperature, so they have what we call internal compensation. They compensate for this. How they do the compensation? We have these schedules. Okay, we call them the lookup table. For every type of sensor, there is a lookup table. This relates the voltage you measure with the temperature. Okay. Now, as I said, you need to know the reference temperature, which is usually the room temperature. But then you need to find the total temperature. It is the V you measure plus the V at the reference. So let's see some typical examples. The voltage difference between the hot and the cold, VD equal to this. So this is the voltage that you measure. This is the voltage difference. But we said that this voltage difference is not the uh, the voltage or the temperature at the hot point. So let's go back here. The V hot equal to the V that you measure plus the V of the reference to start with. Now, how much V of the measurement? This is what you measure, which is 3.409 millivolt. Now, I need to add to it V reference. How to add the V reference? Knowing the temperature. Now, this is the table that convert the temperature into voltage and vice versa. So the temperature is 22. Let's try to read this one. Here is the temperature in this direction and in this direction, and in between this is the voltages in millivolt. So what is the temperature? 22. So this is goes minus 10, 0, 10, 20, 30, 40, etc. Okay, and here it's 0, 1, 2, 3 until you reach 10. So 22, you come here to the 20 and you look for the 2 because 20 is 20 plus 2, and here is the 2. You go down here until they intersect, and this is the value. This is the voltage due to a temperature of 22. So this becomes equal to plus 0.87, and if you add this you get 4.279 millivolt. Now I get the voltage. But my interest now is not the voltage. Remember, my interest is to find the temperature. So we'll come here and we look for 4.279, 4.2. Yeah, luckily we have it. This is 4.2, exactly the same value. 4.279. So this is 100. Here 0. So the temperature will be equal to 100 degrees centigrade. So this voltage that you measure with corresponding to this ambient, this will get you 100. Okay, let me see this one. Here's the question here. Sorry, can you show me how we get the 0.87 again? Okay, now we mentioned that from the previous slide that the V, the voltage due to the hot point equal to the V that we measure, which is due to the difference plus the reference. Okay, now here we have the voltage that we measure is 3.409. We need to add the voltage of the reference, but we don't know the voltage of the reference. Rather, we find the temperature. We know the temperature of the reference. So we'll come here and we look what is the corresponding voltage to this temperature. This is 22. So here's 20 and here is 2. So you go down here, you go this way until you meet here. So this, if for example, if the temperature was 25, so this is 20, this is 5, you go here, and becomes 0.992. If the, let's say the ambient was 15, so you go 10, 10, and 5, and you go this way, it becomes 0.589. As you can see, as we increase the temperature, the voltage, we're getting more and more voltage. Now, once we know this, then we can find the corresponding temperature. If we don't find the exact same voltage, okay, this is an excellent question. Let's assume that we didn't, the voltage that we found was not 4.279. That is, which is actually unlikely that to happen. Let's assume that the voltage was 4.315. That is the voltage that you got, not 4.279. So it means that your temperature is between this and this, between these two values. This number is between these two values. So, so this one, let me do it here. Clean this one here. Okay. So, as I said, instead of 4 point, you're getting any value in between. So this is 4 point, let's say 315. So this is between 4.279 and 4.325. It's between these two values. 4.279 0.79 correspond to 100. 4.325 is corresponding to 101. So you are expecting that this will be something in between 100 and 101. How we can tell the values? So this is an X. So we use what we call is interpolation. In interpolation, you assume this is a linear relation between the points. So you can say the following: 4.325 minus this minus this 4.279 divided by this minus this 101 minus 100. What is this? This is the slope actually. This is the slope. You subtract, assume these are the y and these are the x-axis. This is the slope. Now this will be equal to 4.315 minus 4.279 divided by x minus 100. One equation, one unknown, you can find x. Sometimes some of you says, oh, what is this? This, we don't understand anything. It's very simple. Let me show it to you here in a simpler way. Assume that this is your x-axis, this is your temperature. And this is your y-axis, this is your volt. So we have 3 points. We have the 100, the 101, and that we don't know. So we have 1 point here, another point here, a third point here. So this is straight. We assume that because the points are close to each other, even if the whole curve was non-linear, these 3 points, the relation is linear. So this is will have one slope here that govern these 3 points. What is the slope? Differences in y divided by differences in x. So here in the first one, I took the 2 extreme points here. This is, we know it as 4.279. This is 4.3, and this is the one in the middle, the 4.315. So this minus this, or this minus this, doesn't really matter. This minus this divided by this minus this is the slope of the line. Now, since this point is on the same line, so we assume that the slope between this and this is the same as the slope between this and this. So what is the slope here? Is the difference between these 2 points divided by the slope of including the x. So by equating the slopes, we can get the point if it is in between. So this is called interpolation. I'm quite sure, or I'm hoping that you heard this somewhere in your studies, in math, in anything. Use the word interpolation. We use it a lot in our case. Okay, let's go for the last example here. Assume that we have this voltage difference. Remember, V at hot equal to V that we measure plus V reference. Now, what we measure is 4.472. What is the reference? Now here, the cold junction is at -5. So -5 is my reference point. So where is the minus here? -10 here to 0. So here, if you go back, this is the -5. So it is minus 0.193. And if you do this, this is always will be equal 4.279. 4.279, this is the 100 degrees centigrade. So although these are measurement done at different reference points, you are still getting the same voltage because the difference between the two will be the same. So yours will be equal to 100 degrees centigrade. There's one question here. It says here, what would be -15? No, this one doesn't show. Here is up to -10 only. Okay, so you don't have -15. If you want to have -15, you will have another sheet. Okay, you can't have all the measurement in one sheet. So I just brought the sheet that has the measurement of interest. Now, because this is a data sheet, it comes with many sheets. Depends on what is the temperature you are measuring, then you can use the corresponding one. Remember, we said that in the K type, the temperature difference is 53. If you look here between minus 10 and 110, it is 5.228 millivolt only. So still there are many other sheets available for this. And see here, the 0 is our reference. If you are measuring at 0, then you have 0 volt. So at your point. Let me see here. What is 0.1 0.195? I don't know what do you mean, Abik? If you can, there's no 0.159. This is minus 0.193. There is no 0.195 here. I'm not sure what you are referring to. If you can explain. So this is minus 0.19 minus 0.193. Okay, so I'm not sure. This is at minus 5, not 5. It goes from here from 0 to minus 10. Okay, let me see some question about how we can read this. Let me clean this and let me give you some exercises here how to read this. Let me clean this is completely, erase everything. Let's see that we want to measure different. Let's see here. I want to see the voltage for 26, 34 minus 895. Okay, so let's see what is 26. Okay, here it is in tens, so this is the 20. Then 6, here is the 6. So we go from this one here and one here. So this is the value. It is 1.033 millivolt. Let's look for 34 again. Here's in tens. So this is 30. This is 4, 30. So this is the voltage, 1.362 minus 8. This is minus 10. Here, this is minus 10. This is the 0 now. If you add, so here it is minus 8 will be this, which was minus 0.077. 95. This is the 90. This is the 5. Goes down, goes here. So it is 4.0646. So this is how you can. Hopefully that explains how we can read. Okay. So I will stop here. What is left? We have 4 other sensors. We'll talk about them on Thursday. But I think it's enough for you guys. I know you are busy with other exams, so please go ahead and when you come back, you will not see that there is a lot of material that piles on front of you, so that you can easily catch up. Okay, guys. Wish you all the best and see you on Thursday.